Hello everyone, this is Mr. Kazi here with another lesson for chemistry, and today we're going to talk about quantum numbers. Now the importance of quantum numbers is to understand where the electron is. Remember, we had three questions here. What is the electron? Where is the electron? And how does it behave? Well, we know what it is. We're beginning to learn where it is with the Bohr model and now with the quantum mechanical model. And now we need to understand quantum numbers, and we don't have to understand the deep mathematics behind quantum numbers. What we need to understand is how to use it to understand where the electrons are, and then use that information to understand how electrons behave. And when we do that, we then open the world to naming compounds, chemical bonding, and chemical reactions. And that will bring it all together. And I tell you, if you buy into my system, if you'll buy into the next few lessons, I guarantee you will do better in chemistry than most of your fellow classmates. All right, let's get started. Quantum numbers describe the orbital occupied by an electron. So we want to understand what orbital they're in and where they're at. And now this is going to be very important later when we talk about valence electrons. Quantum numbers tell us four things. They tell us the distance from the nucleus, they tell us the shape of the orbital, they tell us the position of the orbital, and the spin of the electron. And these four quantum numbers help us describe where and how the electrons behave. You'll see it as we go through the lessons. The first quantum number is the principal quantum number. The principal quantum number describes the main energy level of the electron, and that's how far it is from the nucleus. We start with the nucleus, then we have energy level 1, energy level 2, energy level 3, etc. Angular momentum, which symbol is a lowercase l, describes the shape or type of orbital. There are four types of orbitals. There's S, P, D, and F. And S has a numerical value of 0. P has a numerical value of 1, D has a numerical value of 2, and F has a numerical value of 3. And these numbers are used as labels, so that when we talk about what is the quantum number of the L in the S orbital, we say it's 0, or L equals 1 if it's a P orbital, or L equals 2 if it's a D orbital, and F equals 3 or L equals 3 with an F orbital. And so those are our orbital shapes, their names, and their numerical values. You'll notice that we have the S, which is a sphere, and then we have the 3 P's and the 5 D's. And the F's were kind of complicated, so I didn't draw them, but I think I'll give that a shot now that I'm a little bit better at Photoshop. The third quantum number is the magnetic quantum number. It's M sub L for its symbol, and it describes the electron's position in the orbital. S has one possible position, the P's have 3 possible positions, and the D has 5 possible positions, and the F has 7 possible positions. So if you're in any energy level, let's say in order to get to the F's you have to be in at least energy level 4. In energy level 4, you're going to have the F, and there'll be 7 possible positions or orbitals in that F orbital. But if you're in the S type orbital in the 4th energy level, there'd only be 1 position, etc. The 4th quantum number, developed by Paul Dirac, is M sub S, and it deals with relativity and kind of helps deal with the whole idea of relativity in the quantum mechanics. I mean, you have 2 electrons, they should repulse each other, but instead they stay in the same orbital next to each other even though they're both negative, and that's just kind of the difference of the subatomic world. Quantum mechanics was brought out to show the differences in the quantum world and the macro world, or Newtonian physics. So the spin describes the electron spin, plus 1/2 is how we label the counterclockwise, and minus 1/2 is the clockwise. And so the idea here is that one electron is going counterclockwise and the other one's going clockwise. Which one, in reality, we just don't know. This is all a purely mathematical description of the atom. So the mathematics explains it this way. Well, I haven't seen it, and no one has ever seen it. but it works. The mathematics works. It works in our empirical data. So at this point, until somebody comes up with new information, this explanation works of why two electrons can be in the same orbital, even though they're both negative. All right, let's not really dwell on that too much. Let's get going. All right, here's some rules. Energy levels, or sometimes what we call shells. The maximum number of electrons in any one energy level is 2n squared. So if you have energy level 1 squared times 2 equals 2. N equals 2. 2 squared times 2 is 8. And for energy level 3, energy level 4, and energy level 5, nice little equation for the energy level, and so on. The sub-energy levels, the number of energy levels in any main energy level is equal to the value of n. Now you get that? The number of energy levels is equal to the main energy level. So if the energy level is 1, you can only have one type of orbital. That would be S. S being the lower energy. And so then the number for the angular momentum, or L, equals 0, because S equals 0. Let's look at energy level number 2. You can have S and P, or 2 sub-energy levels, and the numbers can be L equals 0 or L equals 1, depending if you're talking about the S orbital or the P orbitals. Let's look at energy level number 3. Now, energy level number 3 means you can have 3 sublevels. Now, I hope you're getting this pattern here. Energy level 3, 3 sublevels. And those sublevels, S is 0, P is 1, and D is 2. So L can equal 0, 1, or 2. Energy level number 4, you can have S, P, D, or F, and L can be 0, 1, 2, or 3. And hopefully you're seeing the pattern there. Those numbers match the values of the sublevels. All right, let's look at the positions. In every sublevel, there are a certain number of positions. So in the S sublevel, there's 1 position. Now, position means orbital. So there's 1 orbital. In the P's, the sublevel has 3 positions, or 3 orbitals. In the D's, the sublevel, there are 5 positions, or 5 orbitals. And in F, there are 7 positions, or 7 orbitals. And so there's just little things that we need to make flashcards for, or some kind of study device, because we just need to know these. You need to know how to figure out your sublevels, and you need to know how many positions are in each sublevel. The next thing is that in each position, or in each orbital, there's a maximum number of electrons, and that is 2. There can only be 2 electrons in any orbital, okay? And so that helps us, because with that number, you can figure out how many electrons are in each sublevel. Sublevel S has 1 position. And by the way, that doesn't matter if you're in energy level 1, 2, 3, 4, or 5. It doesn't matter what S it is. It only has 1 position, and that 1 position is labeled 0 and has 2 electrons. P sublevel has 3 positions, -1, 0, and 1, and 6 electrons total. D sublevel has 5 positions. There they are labeled. Notice the symmetry in the P's and the D's. And there are 10 total electrons. Pretty straightforward. F sublevel has 7 positions, and I bet you could probably already figure out how they're going to be labeled. -3, -2, -1, 0, 1, 2, and 3. 14 total electrons. Pauli exclusion principle. No 2 electrons in the same atom have the same 4 quantum numbers. They might have 2 or 3 of the same quantum numbers, but in the same atom, the spin number will be different. Even if they have the first 3 the same, the spin number will be different. So review. What is the first quantum number? Principal quantum number. What is the description for N? The main energy level. What is the second quantum number? That's right, it's the angular momentum. What is the description of L? Orbital shape or type. How many orbital types are there? There are 4, S, P, D, and F. What is the third quantum number? Magnetic quantum number, and it is m sub L. What is the description of m sub L? It's the electron position. It's the orbital. How many positions in S? 1. How many positions in P? 3. How many positions in D? 5. How many positions in F? What is the fourth quantum number? That's right, spin, m sub S. If you have any questions, be sure to go to www.mrkazi.com and check out that website for more information. And also don't forget to go to YouTube, put in Mr. Kazi, and find my videos and subscribe. And then every time a new video comes out, you'll be notified. Happy ion.